voice because I have a cold. Hopefully it will survive until the end of the day. If not, then I'll show slides and will not talk, and I don't know if it's for the better or the worse, but it will be okay. So the red bar is now here on non-abelian symmetries. So a reminder, yesterday we set 8 rules for constructing Lagrangians. They should be real, they should obey the Poincare symmetry, they should obey internal symmetries. We write usually the normalizable part of the Lagrangian only. It's the leading terms and enough for us at present. Then we gave abelian symmetries, or the concept of symmetries altogether. We said that discrete symmetries lead to selection rules, that global continuous symmetries lead to charge conservation, and that local continuous symmetries lead to the prediction that there are interactions mediated by massless spin-1 mediators. And we saw the explicit example of QED, where the symmetry was U1, and in the beginning we introduced a pair of fermions, left-handed chirality and right-handed chirality, both with the same charge. So Majorana-Mess terms were forbidden, and Dirac-Mess terms were allowed, and we wrote the most general Lagrangian according to that. And we find that this theory describes a massless vector boson that we call the photon, and a charge fermion, Dirac fermion, that we call the electron, and then we extended it to more than one charge fermion, the muon and the tau, etc. So if yesterday was difficult, today will be more difficult. So I'm apologizing, but we are going from phase transformation, essentially, U1, abelian symmetry, to something more complicated, which is the non-abelian symmetry. So I'm not going to teach group theory. See, the things I don't teach here, quantum field theory, and I don't teach here group theory. I apologize for both, but in 5 days I cannot do it all. But I hope enough ingredients of group theory will be clear that we can proceed and understand what is happening. So I'll give a short introduction to non-abelian symmetries. Then we'll see 3 simple examples. I think each of them is 1 slide. Scalars and imposing an SON symmetry, vector-like fermions imposing UN symmetry, chiral fermions imposing UN times UN. The details here are not important. It will demonstrate some concept. And then we come to the very interesting part of local non-abelian symmetries and what they require if we want to impose them, if these are to be imposed symmetries. While there is, one can, in all of this, talk about all kinds of non-abelian symmetries, the standard model, and as far as we know, nature employs just 2 of these, SU2 and SU3, which are the 2 simplest ones. And even in these, only a limited set of representations. We'll say what representations are. And so, in the end, effectively, we do not need the full machinery of non-abelian symmetries, but just what's written here, to which I'll come back later. And talk a little bit about running coupling constants, what that is, because that will be important later. So abelian symmetries are those where applying 2 symmetry transformation, the overall transformation does not depend on the order of which you apply this transformation. You can do transformation A first and B second, or B first and A second. The result will be the same. And it's easy to see that in a U1 symmetry, that's the case. If you do some phase transformation by theta 1 and then another transformation by theta 2, the overall result was be a phase transformation of theta 1 plus theta 2 times the charge. While if you do theta 2 first and theta 1, it will still be the charge times theta 1 plus theta 2. So the order doesn't matter. Non-abelian, so the U1 is the abelian symmetry that we saw yesterday, and it's the one that appears in the standard model. So in fact, it's the only abelian symmetry that is important for our purposes. In non-abelian symmetry, the result of applying two symmetry transformation might depend, not for all transformation, but might depend on the order in which they are applied. So they do not compute. Doing transformation A and then B, or B and then A, might give different results. Depends on what are these transformations, but if there is at least one transformation where the order does matter, then this is a non-abelian symmetry. Okay? Good. Yes?
Please put the mic up.
Yeah, I'll be careful today not to talk much louder because that will enhance. And and the two non-abelian symmetry groups that are important, that appear in the standard model, that seem to apply in nature, that we know apply, maybe there are larger symmetry groups, but we don't know that, are SU2 and SU3, and we'll soon see what these are. So, what is an SUN symmetry transformation? It's a unitary transformation. Phi is some vector if you want. It has several components, phi 1, phi 2, it's a doublet, or phi 1, phi 2, phi 3, a triplet, or longer ones. And it's transformed by unitary transformation. So you can think of this as if this is, let's say, a vector of two components, that this will be 2 by 2 matrix times this phi. So that's the transformation, not just a phase transformation. Phi has now several components, and U is a matrix of the appropriate dimension. Okay, so if phi is a triplet, if it has 3 components, then U is a 3 by 3 matrix. But these U's are not any matrix, but unitary matrix, namely U times U dagger, okay, transpose and complex conjugate, equals U dagger U, equals a unit matrix. With such transformation, if you started, which I presented yesterday, then also after you transform the field, the Lagrangian will remain with canonical kinetic terms. Okay, so we do it with unitary transformation because we want to keep the canonical normalization of the kinetic terms, which is the normalization by which the other terms in the Lagrangian can be interpreted straightforwardly. We know what they mean. So, a field phi in a representation, okay. So representation can be a doublet, a triplet, and dimension m. So a doublet has m equals 2, a triplet, 3 components, m equals 3, and there could be several r with the same m, so that's why I do not call necessarily the representation by just the size of it, okay? So, if I have some phi with 2 components, let's call it phi 1 and phi 2, then R is called a doublet, and M is 2, the number of components here. And if there are 3 of these, then I call R a triplet, and M equals 3, etc. we will not need to go much above that, as we will soon see. So there is a lot of notation here, but that's what it means. And then this is how the transformation law under SUN looks. The component, so phi I, so if it's a doublet, I can be 1 or 2. 1 or 2. It's the component within this vector transform into e to the I ta theta a. So theta a are the same kind of thetas. These are rotation angles, okay? It's a parameter that for any theta, this is a SUN transformation. Ta are fixed matrices of the size that depends on what is the dimension of the representation. For doublets, Ta would be a 2 by 2 matrix. For triplets, Ta will be 3 by 3 matrix. For octets, which is a vector of 8 components, Ta will be 8 by 8 matrices, etc. And Ta are real numbers. Okay, function. Okay, in a local symmetry, functions of spacetime. In a global symmetry, just real numbers. So if these Ta are m by m matrices, then so is e to the I ta theta a. So this U is always can be written in this form. The most general U, unitary matrix in under SUN, can be always written with this U. So the indices I and j, this is an m by m matrix. It depends on the size of the vector phi on the representation. So they go from 1 to m. But here, this A, enough to span all of these possible transformation in SUN is to have A go from 1 to n squared minus 1. So SU2, n is 2, okay, n is the number here, and n squared minus 1 is 3, 2 squared minus 1. And so here you have 3 fixed matrices, if you want, T1, T2, and T3. A fixed number of matrices. Their size depends on which kind of representation they act upon. So, if phi is a doublet, Ta are T by 2 matrices, and with SU2, there will be 3 such matrices. And so, for SU2, with this is a doublet, there is e to the I T1 theta 1 plus T2 I T2 theta 2 plus I T3 theta 3. Okay, so the number of TAs is n squared minus 1. It depends only on which group we are talking. The matrices which represent them depends on which field they act upon. Their size is m by m if they act on a representation of dimension m. If you're still able to follow me, then I can continue. So just another example, which is almost all we need. If we have SU3, n is 3, and we have a representation that is a triplet, so there is phi 1, phi 2, and phi 3, vector column, then the number of TAs is 8, 3 squared minus 1, we are talking about SU3, and if they act on the triplet, they are represented by 3 by 3 matrices. No matter what size of matrices the TA appear here, which depends on this, they are always fulfilling this commutation relation which characterizes the group SUN. So two of these, TA, TB, equals I, FABC, TC. So first of all, FABC are known numbers, fixed numbers, which only depends on the group SUN that we are talking about. For example, and A and B and C, these indices run from 1 to n squared minus 1. So for example, for SU2, there are 3 generators, these TA are called the generators of the group. And for SU2, these FABC are the antisymmetric tensor epsilon ABC. So epsilon 1, 1, 2 is 0, epsilon 1, 2, 3 is 1. These are known numbers. Okay? For each group, these are known numbers. So, a lot of notation and names. So these TAs that appear here are the generators of the group. SU2 has 3 generators, SU3 had 8 generators, and we will not need to go beyond that. So, let's see a little bit the differences between abelian and non-abelian symmetry group or transformation. If phi is charged under a U1, so it does transform under a U1 transformation, it must be complex. The transformation law is phi goes to e to the iq theta phi, where q is the charge, called it, and it's a real number. And the transformation law is defined for each single complex field separately. So we must assign a charge for each field, and that charge tells us how it transforms. And for the Lagrangian to be invariant under a U1 transformation, the sum of charges in each term in the Lagrangian must be 0. Because the whole term transforms like e to the I, sum of all charges of the fields that appear in that term, times theta. And if the sum of all charges is 0, it's e to the I 0, which is 1. Still with me, I hope. With non-abelian symmetries, as I said, I promised it will be a little bit more difficult. There are complex representations, there are real representations. Okay. One point about group theory. Each representation has an inverse. So, an inverse means that the representation times its inverse includes in it the unit transformation. Okay, that things do not transform. If you have a product of a representation and its inverse, then this product does not transform. One of them is e to the iq I theta a ta, and the other is e to the minus I ta theta a. Something like that. If R real means that the inverse is the same representation. So a doublet times a doublet of SU2 includes in it a singlet plus a triplet. So it includes a singlet, that's a real representation. In SU3, 3 times 3 does not have in it the singlet representation. So if you have a product of 2 fields, both of them triplet, then this will not include a singlet in it. There is another representation of dimension 3 called 3 bar in the language, and 3 times 3 bar does contain a singlet, and since 3 bar is different from 3, then this is a complex representation. Okay, the transformation law for SUN symmetries looks like this, with TA are n squared minus 1 generators of the group. I runs from 1 to the dimension of the representations in which phi is, a triplet. I runs from 1 to 3, and the TA are m by m matrices for m-dimensional representation. And the transformation law is defined for, let's say, a doublet or a triplet, for each doublet, each triplet separately. And for L to be invariant, the various representations of a field that appear in a term, let's say 3 times 3 bar if you have 2 fields, or 3 times 3 times 3, for example, if you have 3 fields, must have in it the possibility of a singlet. That this product does not transform at all under the symmetry transformation. Each of the fields does, but the product of them does not. Okay, it's more complicated, it sounds more complicated than it really is. And when we start doing examples, you'll see that it's not as complicated as in this general writing. We could have product groups. For example, not just SU3 or SU2. We saw product groups also in the abelian case, right? We had U1 times U1 and other things. You could have, and the standard model does have, SU3 cross SU2. And the way we write a representation under a product group or non-abelian groups is the following. For example, we write for a triplet under the SU3 and a doublet under the SU2, we write, the notation is phi 3, 2. 3 is the size of the representation, or the name of the representation under the first factor in the product group, and the second number is the representation under the second group in this product group. And so we can write phi as having, if you want, 6 components, write it, and the convenient way of writing is writing first the index under the first group and then the index under the second. So phi 3, 2 has 6 components. Alpha runs from 1 to 3 because it's a triplet under SU3, and I runs from 1 to 2 because we assigned it to a doublet of SU2. So that's the way we write. And then the transformation law is the following, and I wrote it here because for reasons that I'll explain in a minute. So there is a transformation law under the SU3. Alpha and beta run from 1 to 3, and here is I over 2 lambda A theta A. Lambda A are 3 by 3 matrices, and there are 8 of these. A runs from 1 to 8, the number of generators of the group, n squared minus 1, and each lambda 1, lambda 2, lambda 3, lambda 4 is a 3 by 3 matrix. Actually, these are known matrices, okay? These are matrices of 6 numbers. They are called the Gelman matrices. So these are 8 known matrices, and this is how a triplet under SU3 transforms. A doublet under SU2, the index I runs from 1 to 2, the index J runs from 1 to 2, the index B runs from 1 to 3, n squared minus 1, n is 2, SU2. And so there are here 3 matrices, tau 1, tau 2, tau 3. Each of them, for phi transform is a doublet, is a 2 by 2 matrix. Actually, you may know these matrices. These are the Pauli matrices. You know them sometimes as sigma x, sigma y, sigma z, or right, sigma z is 1 minus 1 on diagonal, sigma x is 1 and 1 off diagonal, and sigma y is minus I and I on the off diagonal. And that's because SU2, you may know it because SU2 is the group related to spin, and that's related to how spin transformation go. But here we are talking about internal symmetries, nothing to do with space-time. Now, the smallest representation under each group, except for a singlet means something that does not transform, what we call neutral. For an abelian symmetry, we call a singlet for a non-abelian symmetry, something that doesn't transform, remains itself. So the simplest non-singlet groups are of the size of n. So the simplest or the smallest representation of SU2 is a doublet. And the smallest representation, smallest dimensional representation under SU3 is a triplet. Turns out that in the standard model, or all the particles that we know, standard model has only 2 non-abelian groups in it, SU3 and SU2. And all the scalars and the fermions are either singlets of these groups or in this smallest representation. So all the fields of the standard model, fermions and scalar, are either singlets or doublets of SU2, and all the scalar and fermion fields of the standard model are either singlets or triplets of SU3. These are the only representation that so far we need in order to describe nature. And that explicit transformation law of triplets are written here. A singlet goes to itself. The transformation law of a doublet of SU2 is written here, and a singlet goes to itself. That's all that we need to know as transformation law for the standard model fields, okay? So from all this formal introduction, in the end, this is what you have to remember. I wrote it here, so you may remind yourself. Under SU2, all the scalar and fermions are either singlets, so phi goes to phi, or a doublet, so phi has 2 components under SU2, and it goes, phi I goes to e to the I over 2, tau b, Pauli matrix, theta b, a real parameter or a function of phase space of space-time, when we talk later about local symmetries, ij, phi j, I and j runs from 1 to 2, b runs from 1 to 3. All standard model fields under SU3 are either singlets, phi goes to phi, nothing happens to it, or a triplet, there's 3 components, phi 1, phi 2, phi 3, and phi alpha, alpha goes from 1 to 3, goes to e to the I over 2 lambda a, theta a, the alpha beta. So this is a 3 by 3 matrix, alpha beta component of it, phi beta. And a here runs from 1 to 8, and lambda a are the Gelman matrices. That's all you need from all this long introduction to do later the physics of the standard model. Let me add that these are the representations of the scalars and fermions. In addition, when we introduce local symmetry, we will see that we will need get all the vector bosons. We need vector bosons, and they must be in another representation called the adjoint representation. That's the representation of dimension n squared minus 1 for SUN. So for SU2, n squared minus 1 is 3, 2 squared minus 1. So the vector bosons will reside in a triplet representation. For SU3, the adjoint representation, n squared minus 1 is 8, and the vector bosons will be in an octet, the 8-component representation of SU3. Now that's it. So scalars, fermions, and vector bosons of the standard model are in 3 possible representations: the singlet, the fundamental, the one with the lowest dimension, a doublet for SU2, a triplet or anti-triplet for SU3, and the adjoint for the vector bosons, the n squared minus 1 dimension representation. These are all the representations of the standard model fields are in these 6 kind of things, and later we'll see exactly what they are, but this is the group theory really that you need in order to understand the standard model. So, again, some notation. If we have a group, for example, SU3 cross SU2, and I assign phi to the 8-1 representation, what I mean is that it's an octet, 8-component representation of SU3 and a singlet of SU2. If I have a product of non-abelian group, SU3 times U1, then I write the representations as, in parentheses, the representation under the non-abelian group, and as a sub-index, the charged under the U1. That will always be my notation. And this is the group of the standard model, as we will later see, SU3 times SU2 times U1. So I have 2 numbers in parentheses. These are the representations under SU3 cross SU2. So this is a triplet of SU3, a doublet of SU2, and the charge under the U1, I write as a sub-index, in this case, plus a 6th. Believe it or not, there is such a representation in the standard model, so this is actually something that seems to apply in nature. This is one of the representations of the fermions in the standard model. Good. So that was group theory in half an hour. And hopefully, at the end, when we see that all we need is just this list, it's not as threatening or intimidating as it might sound at first. In particular, if you never heard of Lie groups, SUN, etc., then this is heavy, but effectively, for what we need just these things here. 3 examples, just to demonstrate a few features that non-abelian symmetries can and cannot do. So let's start with scalars and SON. I impose a symmetry that is called SON. I lost no more laser, okay, I think. I continue with my finger, so that's my laser now. No fermion fields and a single scalar field phi in a representation of dimension n. Now this is another thing of language which is important, at least for me. This field has n scalar degrees of freedom, okay? There is phi 1, phi 2, phi 3, dot, 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 up to phi n. Okay, so if this is SO3, then there is phi 1, phi 2, phi 3. It has 3, but I call it a single scalar field. Okay, I don't call it 3 fields. If it is one representation, I call it a single field. Okay, and actually it has a meaning, because the meaning that we have, let's say 3 components, means that there is a symmetry, and under this is a single representation, means that we cannot distinguish between these 3 components. We cannot know whether what participated in a particular process that we measured was phi 1 or phi 2 or phi 3. That's the meaning of symmetry. Symmetry is the inability to distinguish. When we say, I have heard it, that a quark has 3 colors, okay? These are names. We never know whether the quark that participated was red or blue or green. All we know that there are 3. But which of these we don't know. That's what the symmetry means. And so even in that sense, it's the right way to call it a single field, and not count the number of the components within the representation. So there is a single real field, and the most general Lagrangian, this is a scalar. The thing that is forbidden, okay, is 3 linear terms. You cannot take 3 representations n and contract them to a singlet. But yeah, so phi t phi, what is meant by this is phi 1 plus phi 2 plus phi 3. This combination, even though each of phi 1 is transformed, this combination is a singlet of SON. So this combination under an SON transformation remains the same. So these are the only types of things that you are allowed to write when this is the symmetry group and phi is in the fundamental representation. There is a single quadratic term. You see all components here. So this is m squared times phi 1 plus phi 2 plus phi 3. And it's the mass squared term. Right? We said that the quadratic term. And it means that all 3 components have the same mass. This goes along with what I said. You cannot distinguish them. There is a symmetry. You cannot know. You measure the mass. You don't know if it was phi 1 or phi 2, phi 3. They have the same mass. And also the quartic term depends just on this possible combination. And the reason I write it is the same that I did for abelian symmetry. There is no way by an internal symmetry to forbid mass square terms. Okay? We don't have this kind of imposing a symmetry in order that to explain massless scalars. Come back to it later. For SO2 and the doublet under SO2, the symmetry is actually abelian, and we've seen it, okay? We've done SO2 transformation. We talked about phi r and phi I and required that they are invariant under SO2. So SO2 is not a non-abelian, but from SO3 and above, it is. Second, again, the details of the group theory here are not important because the symmetries that I give here are not symmetries that apply in nature. I just want to demonstrate. So I wanted to demonstrate that mass squared terms for scalars cannot be forbidden by symmetry. Here, the lesson will be that Majorana mass terms for fermions can be forbidden not just by an abelian symmetry, when they carry a charge, but also by a non-abelian symmetry when they are not singlets of the non-abelian symmetry. So let's impose the symmetry UN, which has a non-abelian component, SUN. It's the same as SUN times U1, non-abelian times abelian, with n larger or equal to 2. And I assign a single left-handed fermion into the fundamental representation, the representation of size n under the SUN, and carry charge +1 under the U1, and similarly for psi right. And no scalar fields. So this is the most general Lagrangian. And again, what is meant, for example, by psi left bar, psi right is psi left bar 1, psi right 1, plus psi left 2 bar, psi right 2, up to psi left n bar, psi right n. And this contraction is exactly the contraction. So this, under UN transformation, does not transform, remains the same. So first of all, psi left and psi right are charged, let's say, under the U1, which means we cannot write Majorana mass terms. Okay? They would violate this U1. And on the other hand, they transform in the same way under the symmetry, the left and right-handed. So they can be combined. So we can write a Dirac mass term, and we can combine them into a Dirac fermion psi. And in the language of that Dirac fermion, then this Lagrangian looks very simple. It's exactly the same as this. This is a Dirac fermion, kinetic term, and it has a Dirac mass m. So that's to show how to forbid Majorana mass terms, and we can also forbid Dirac mass terms if you want. So a little bit more complicated symmetry, UN left times UN right. Left and right are names. So this is SUN cross U1 times SUN cross U1. And the left-handed field I now assign to the n-dimensional representation of SUN left and charge 1 under U1 left, and a singlet of the UN right. Singlet carries charge 0 under SUN right and U1 right respectively. And the opposite I do for psi right. So now, first of all, both are charged under one of the factors here. And second, they transform differently under the group. One of them transform under UN left, the other under UN right. There is no way to write a product of them that is a singlet of the entire group, and therefore also the Dirac mass terms are forbidden, and all you can write is the kinetic terms. And so there is a way to explain masslessness of fermions also by non-abelian symmetries. If they transform non-trivially, they are not singlets, then there is no Majorana mass term. And if it's a chiral theory, left and right cannot be matched into a pair that transform in the same way, then also Dirac mass term is forbidden. So you can do it with an abelian or non-abelian symmetry. Okay, local symmetries. Yesterday we saw what I find to be an amazing concept, that if you insist that the symmetry is local, then you have no choice but to introduce a spin 1 field or a vector field into your theory, and with specific transformation properties. And for non-abelian symmetries, it's even no less predictive than for the abelian case, and there is another interesting ingredient in that. So first of all, you may have heard the name Young-Mills theory. I don't know, it's a famous term. Young-Mills theory are theories of local non-abelian symmetry. So just a name for that. I'm not even sure that historically Young and Mills were the first to introduce local non-abelian, but they did it in the first time that was relevant to what later became the standard model and its extensions. And the same as in local abelian symmetries, terms in L psi, the part that has only fermions in it, just Majorana, Dirac masses, that's all that is allowed. L phi, the scalar potential, most generally quadratic, trilinear, and quartic terms. L Yukawa, the part that has 2 fermions and a scalar in it. So all of these parts do not have derivatives of fields in them. So similarly to the abelian case, if they are invariant under the global symmetry, they are also invariant under the local symmetry. Okay? If they are invariant under global SU3, they would also be invariant under a local SU3. Okay, global symmetry is always part of the local symmetry, not the other way around. Okay, so, right, because if you have e to the I Ta theta A of x, then theta A of x could also be a constant of x. This is the global part of the local symmetry. But local symmetry is not part of a global symmetry. It's different. However, the terms in the Lagrangian that have derivatives in them, which is the kinetic terms, they are not invariant under the local symmetry, also for a non-abelian symmetry group. And still, I now want to insist, I want to have dynamical fermions and dynamical scalars, things that represent particles that can propagate in space-time. I must therefore have kinetic terms. And I insist on having a local non-abelian symmetry. There is a way to do it. As I said yesterday, at first sight it looks crazy, but since nature makes use of this, then we go along with this. And again, there is only one way to do it. So let us see. So here is the transformation law of any field under an SUN symmetry transformation. Phi goes to e to the I Ta theta A of x times phi. And when we do d mu phi dagger d mu phi, the kinetic term, or psi bar gamma mu d mu psi for fermions, then when d mu acts on this, it acts not only on phi, but also on theta, and the terms with d mu theta are the ones that violate the invariance, and we have to fix for that. We have to remove them by some trick from the Lagrangian. We must have the d mu phi in the Lagrangian because we want to describe free propagation in space-time, so we have to fix for the non-invariance of d mu phi dagger d mu phi, and we will be able to do it if we can replace this space-time derivative d mu with something that is called covariant derivative d mu. D mu must have in it this del mu because we want to keep the kinetic terms, and we can add something else that again transforms like a vector of space-time. Has to have well-defined transformation properties under space-time if we want the Poincaré group to remain an invariance of our Lagrangian. So it's clear that what we have to add is something that transforms like a vector, has these 4 mu indices in it. Now, here there is more than that. E to the I Ta theta A means that we have here n squared minus 1 independent transformation. Okay, there is here theta 1, theta 2, theta 3 for SU2, just theta 1, theta 2, theta 3. For SU3, we have 8 of these. So we have, let's say in SU2, 3 independent transformation for 3 independent, if you want, parameters here. And for SU3, we have 8 independent, and we have to compensate for each of these. So, yeah. So it's a reminder that TAs are n squared minus 1 generators, phi m-dimensional, TAs are m by m matrices. So what should we do? So if we want to compensate for d mu acting on each of these theta A, so we have to restore the local symmetry for n squared minus 1 independent rotation. And second, the thing that we have not only to transform in a well-defined way under space-time, so that is a vector, it is also to transform in a well-defined way under the group that we imposed. Everything in the Lagrangian must have well-defined transformation properties under a symmetry that we impose, or else the Lagrangian will not be invariant under the symmetry. And so This suggests that we need to add n squared minus 1 vector bosons, one for each independent non-invariance of the d mu theta a terms. And there is a representation always in SUN of dimension n squared minus 1. That's called the adjoint representation. A triplet for SU2, an octet for SU3. If you want for SU4, the 15 component representation, etc. So, 24 representation, 15 for SU4, 24 for SU5. This 24 for SU5 is a little bit more famous than SU4 because in grad unification there is often a use of SU5 and then it's a local SU5 and you have to introduce vector bosons in the 24 representation. So the fact that we have to add n squared minus 1 of these and they have to transform in a well-defined way under SUN suggests that we must put them in the adjoint representation of SUN. And so the way to do it is to add vector bosons that are in the adjoint representation of the group. Vector boson under spacetime, adjoint under the internal symmetry group. And the transformation law that compensates for the non-invariance of the kinetic terms and transforms like the adjoint representation is this: G mu A goes to G mu A minus F ABC, the structure constant of the group, which are known numbers for each group. Theta B G mu C minus 1 over G d mu theta A. Two things here. First, this minus 1 over G d mu theta A is similar to what the transformation law of the vector boson that we added in the abelian case. This thing here has no equivalent in the abelian case. This is very important for two reasons. First, this last term is a little bit confusing if we want to understand how the field transforms under the internal symmetry group. But the real thing that you have to do is look at the case, the global case, which is, as I said, a particular specific case of the local group. So put theta A to be constant. In the abelian case, the field goes to itself. The photon field, if you put theta A to constant, goes to itself, which means that the photon field does not carry electric charge. Okay, I mentioned it yesterday, but I didn't really explain it. You see it when you put theta A to a constant. You see the transformation property when you put these thetas here to the global case as constant of space-time. While G mu A does transform also in the global case. It has this additional term. It does not go to itself. And this additional thing is the thing that tells us that it transforms in the way that is right for the adjoint representation. This is not something that you can see immediately from what is written on the board. Okay? It's an exercise for homework that does take half a page to prove that this is the right transformation law for something in the adjoint representation. But it comes from this additional term. The second thing is that the fact there is this additional term has significant consequences compared to the abelian case. We mentioned that the photon at 3 level, at least, does not have self-interaction. There is no term in the Lagrangian that has 3 photons in it or 4 photons in it. So there are no self-interactions. Because of this extra term, for the non-abelian gauge fields, there will be self-interactions, and that has further consequences, as we will see. So, we must add gauge bosons. These are vector bosons in the adjoint representation of SUN if we impose a local SUN symmetry. Once we added them, they appear in the covariant derivative, acting on all the fields that transform non-trivially under the non-abelian group. Those fields that are not singlets of the non-abelian, they will appear there. But can we add other terms? Because we said every allowed term should be there. So we added a new field. Can we have additional terms with this G mu nu A mu? Turns out that yes. To find something that is invariant under Poincare and invariant under SUN and depends on the G fields, we define something that we called field strengths, G mu nu A, which is d mu G nu A minus d nu G mu A minus G FABC G mu B G nu C. In the abelian case, we have d mu A nu minus d nu mu, but we did not have this extra term. This extra term relates to this additional thing in the transformation law of the SUN gauge bosons. And now we have, this is what we can add. This and only this is the allowed term, which is both Poincare invariant or Lorentz invariant if you want, and invariant under the SUN local symmetry. No other terms here. And in this term, because of this extra thing, there will be terms which are not just kinetic terms, but also terms that include 3 or 4 fields of this. We will soon write them explicitly, and that's called self-interactions. So this is almost the most general renormalizable Lagrangian that involves only a vector field in the adjoint representation and is invariant under the local symmetry. This star here, the almost most general, is because we can add also such a term, epsilon nu ni rho sigma, G mu nu A, G rho sigma A. We made a comment on this yesterday about the abelian case, and we said it has no physical consequence in the abelian case. Okay, it's a total derivative, and total derivatives can be changed into the values of the fields at infinity, which we usually assume is 0. It's not true for non-abelian fields. This term does have physical significance. This is the source of something called the strong CP problem. We do expect such a term to arise. We expect it to have a coefficient in some convention of order 1, which would lead to electric dipole moment of the neutron that is some 10 orders of magnitude above the current upper bound on that. And that's a puzzle, but maybe I don't think I will come back to it, so I just mention it. I will not include this term because for no other thing it has any significance. So this is the Lagrangian terms that are made purely from vector boson in the adjoint representation of the SUN group. Once we have it, it has a kinetic term for the adjoint for this gauge boson. So these gauge bosons are now dynamical fields. There are physical particles related to them, and the one example that is best known is the gluon for local SU3 that is imposed. So the gluon is a vector boson field in the adjoint, the octet representation of SU3. And we'll come back to it when we discuss QCD. This quarter here is a convention, that's the canonical normalization. You put a quarter here, you know how to interpret all the other terms and do your calculations straightforwardly. Very important, in this combination, there is no mass square term for the gluon field. I now call it a gluon field, okay, but it's any vector boson, gauge boson for SUN group. So such a term, which is invariant under the global group, is not invariant under the local group, so it's forbidden. So we have a very detailed prediction. You want invariance under local SUN, you must have a vector boson in the adjoint representation that is massless. All 3 properties come just from the requirement of invariance under a local non-abelian group. Okay, vector boson, adjoint representation, massless. But this combination does have in it a dimension or things that involve 3 gluons, 1, 2, 3, and 4 gluons, 1, 2, 3, 4. So vertices like this, there was nothing like that for the photon, and vertices like this, there was nothing like that for the photon, but the gluon or the vector field in the adjoint representation of SUN does have such self-interactions. And it's interesting phenomenology, it's interesting for confinement, asymptotic freedom, other things that you may have heard the names. We'll come to them a little bit later. If you have a product group of local symmetries, then for each factor in the product group, you have to introduce its own set of gauge bosons. So if you have SU3 local, you impose local SU3 cross to SU2 cross U1, as you do in the standard model, then you have to introduce 3 fields of vector bosons. For the SU3, it is an octet of SU3, the adjoint representation, a singlet of SU2 and no charge under the U1. That would be the gluon field. And again, it allows you this covariant derivative, or there is a single parameter related to that, let's call it G3. For the SU2, you must introduce a singlet of SU3, a triplet, again, the adjoint of SU2 of charge 0 with another free parameter in it, G2. And for the U1 factor, you must, like a photon field, introduce something which is a singlet under the whole group and allows another independent parameter. So each factor in the local symmetry has its own vector boson. Okay, so we will demonstrate it soon with QCD, which I hope will make it a little bit simpler than this almost abstract ideas. But one more thing, a running coupling constant. So this G1, G2, G3, yesterday we saw that this independent parameter is the strength of the interaction of charge in QED, of the charged fermions with the photon. Here it's the same, this, okay, maybe I should have said it before. G3, in the standard model it will get a name, call it G strong, but G3, when you write it in the covariant derivative, or let's say a fermion field, then it signifies the strength of the interaction of the gluon field with pairs of fermions that transform under the SU3. This G2 characterizes the strength of interaction between these vector bosons and pairs of fermions or of scalars that transform under the SU2. And this G1 characterizes the strength of interaction of this vector field with pairs of scalars or fermions that are charged under the U1. Okay. Now this G1, G2, G3, when you measure them in a process, then their value depends on the energy scale at which this process takes place. It changes from one energy scale to another, and this change is called, or what the term that we use for it is coupling constants run. Run meaning they change their value. And there is an equation that describes that. Mu is the energy scale at which you measure the coupling constant, and the derivative of the coupling constant with respect to the log of the energy scale is a function that depends on the model that you are dealing with, and this function is called the beta function. And okay, I will not go into details, but for a U1 symmetry, and let's say that all your fields have the same charge 1, then beta of G is the number of such fields times G1 to the cubed over 24 pi squared. And the important thing is that it has a positive sign. For SUN, I said the only thing that we have are either singlets or fundamentals in nature. The singlets do not affect the running because they do not couple to the gauge boson. But the fundamental do. If we have a number of copies of such fundamental, then this is how the running is. N, again, just depends on the group. So for example, with SU3, this second term is minus 33, and the first term depends on how many fundamental fermions you included in your theory. But if this NF is smaller than 16, then this is negative. This is always positive. This could be positive. This is always positive. This could be positive or negative, depending on the number of fermion fields in the fundamental representation that you introduced. Okay, the details here are less important. The important thing is that when this is positive, the lower the energy scale, the smaller the coupling constant. So for example, for electromagnetism, when you measure the coupling constant at the scale of the electron mass, it's 1 over 137. When you measure it at a much higher scale, mz, the mass of the Z boson, it's 1 over 128. So it becomes smaller and smaller the lower the energy. That allows perturbative calculation no matter how low energy we go. For SUN, it can assume either sign. If the sign is negative, it means that the lower the energy scale, the larger the coupling constant becomes. And then at some point, this coupling constant will become so large that you cannot expand your calculation in the value of this, because the next term will be larger than the previous. You cannot do a perturbative calculation, and there are physics consequences to that. But for theorists, we just say we cannot calculate, but in phenomenology, it leads to the phenomena called confinement that I will describe soon. Okay, let's skip this. And so these are the basics of non-abelian symmetry, and now we will see a model that implements that and moreover is relevant to nature. So we saw QED as an example of local abelian symmetries, and now we will do QCD, the model of the strong interactions, as an example of non-abelian local symmetry. Okay, so QCD. I'll define it. So I do the same process that I will now repeat and repeat again and again. Define the model. Write the most general Lagrangian, normalizable Lagrangian, consistent with the definition of the model, and then see what is the phenomenology that comes out of that. The spectrum, what are the mass eigenstates, the interactions, how many parameters, what they are, and in the case of QCD, we will explain what confinement is, accidental symmetry, and if time allows, then it's a little exercise, do QCD plus QED, and if not, then we will skip that. So here again, it's a very simple definition of the model. So the first thing is to impose a symmetry, and the symmetry is a local SU3. And I give it a name, this sub-index C is SU3 color. That's how we call specific SU3 for this model. As far as mathematics is concerned, it's just SU3. And the fermionic content are 6 left-handed fermion fields that transform as a triplet, the fundamental representation of SU3, and 6 right-handed fields that also transform as triplet under SU3. Okay, so again, the number in parentheses here is the representation under SU3, which is the triplet representation. The index I here is the number of such fields that I introduce, 6 of each kind. Why 6? Because inspired by nature, okay? That's what we think we have in nature. And from here on, when we have fermion field in the triplet representation of SU3, we call these quarks. Okay, so that's the definition of what quarks are. Fermions in the triplet representation of SU3, and that's why I call them Q and not psi. Okay, we call them psi, but Q because I now call them quarks and no scalars. So this is the definition of the model. And now said, okay, we have to find these 4 parts of the Lagrangian, kinetic terms, purely fermionic, scalar potential, and Yukawa terms, the harmonizable terms in each of these that are allowed for these 6 left-handed and 6 right-handed fermions, each in the triplet representation of SU3. But the first thing, so this is almost automatic now, this procedure. The first thing, I imposed a local symmetry. So I must introduce a gauge boson field, and it requires that this gauge boson is in the adjoint representation of SU3, the octet, and so it has this index of a vector boson mu, and this index A from 1 to 8 for octet of SU3. This is a necessary part of imposing local SU3, and I give this field a name. I call it the gluon field. Okay? Also, everything here is automatic, okay? It's automatic in the sense that I cannot play games. This is all necessary for the invariance under a local SU3. So I introduce the field strengths, d mu g nu a minus d nu g mu a minus gs, that's the independent parameter, and S stands for strong because this will lead to the strong interactions. FABC, the structure constants of SU3. So each of these indices, A, B, and C, runs from 1 to 8, and each combination of this, it's a known number. It comes from SU3, okay? It's not free numbers, these are known. This is a free parameter, GS, that should be fixed by experiment. The model doesn't tell us its value. Only experiment can, and then these 2 fields. The covariant derivative, in order to preserve invariance under local SU3, d mu is del mu plus I gs, again this coupling constant here, g mu a, this octet of gauge bosons, LA. LA are the generators of SU3, so there are 8 of them, always n squared minus 1. They obey this commutation relation. Again, the structure constants are here. This is again SU3 group theory. There is no freedom here. But it's represented by matrices whose size depends on which field they act. So when the covariant derivative acts on these quark fields, all of which are triplets of SU3, it's represented by 3 by 3 matrices. And these 3 by 3 matrices are known as the Gell-Mann matrices. Okay? These are known matrices. You can find their values in books about this. So some of us know the Pauli matrices by heart. I'm not sure I know a particle physicist that knows the Gell-Mann matrices by heart. It's 8 matrices and not 3, it's 3 by 3 and not 2 by 2. Just difficult to remember. I do remember the first 3, okay? Because the first 3 are just the Pauli matrices, if you want, and nothing else. So the Pauli matrices in the upper left corner. So lambda 3 is 1, minus 1, and the rest are zeros, okay? So that I know. That's it. That's what I know. Some people may know more because there are 3 SU2 subgroups hiding there too, and if you remember where they are, then you can tell. There is also 1, 1 minus 2, right? That's lambda 8. Okay. So my memory improves as we go along, so I already know 4 of these. Okay, that's it, I think, anyway. So, known matrices, and d mu acting on Q is del mu plus lambda A over 2. These are the generators in the triplet acting on the triplet representation, the gluon field, and this parameter. It's the same parameter here and here. The same parameter that appears in the transformation law under SU3 of the gluon field. So we have just this one parameter everywhere. So here is the Lagrangian for the model that I presented. L kinetic, the kinetic terms for all the fields. So this is for the gluon field. This is for the left-handed quark fields. This is for the right-handed. And d mu is what's written here. This is d mu acting on Q. That's what it means when I say here d mu on Q. And Ga mu nu is what is written here. So everything is fixed up to this single number Gs, which I need experiment. Everything else is dictated by the local symmetry. Okay? The only thing that is unknown in all these kinetic terms is one parameter. So I have all of these kinetic terms, 6 here, 1 here, okay? 13 kinetic terms. There is one free number to be fixed by experiment, characterizing all of them. Q left and Q right, the triplet of SU3 is a complex representation, means that 3 times 3 does not contain a singlet. There is another representation of dimension 3 bar. So Q left bar and Q right bar are in the 3 bar representation. So since it's a complex representation, you cannot write Majorana mass terms. Majorana mass term is twice the same field, Q left. That does not have a singlet, has anti-triplet and a sextet. Does not have, so 3 times 3 is 3 bar plus 6. 3 times 3 bar is 1 plus 8. And the 1 is what is of interest to us. So anyway, you cannot write Majorana mass terms since you can match all the Q left and Q right to pairs, transform in the same way, right? They're all triplets. Then you can write Dirac mass terms. So in general, it's a 3 by 3 matrix that you can write. For each of the Q left and the Q right, there is an allowed Dirac mass term and no scalar field, so no L phi and not Lu cover. This is the Lagrangian. Now, again, we go into the discussion and the good question from yesterday of what's the number really of parameters. We start from a mass matrix that is complex 3 by 3, and we'll end up, 6 by 6, and we'll end up with much fewer physical parameters. So I do the same trick as yesterday. This is the most general thing I could write. I write it again, and I introduce unit matrix here and unit matrix there. So it's the same Lagrangian, okay? But it allows me to change basis for the same Lagrangian. So these V said are unitary matrices, meaning that V dagger V is 1 and V right dagger V right is also 1. So the same physics, the same Lagrangian. And I choose, however, this V left and V right in a specific way, in such a way that V left MQ V right dagger, called in the language B unitary transformation of MQ, I can always bring it to a diagonal and real form, a 6 by 6 matrix that have only diagonal entries and all of them are real. I can always do it, so that's what I do, which means that I change basis from, in the new basis, the basis where this mass matrix is diagonal and real, I give names for that particular basis to the left-handed quark fields. I call them up left, down left, strange left, charm left, bottom left, and top left. And I give names in this particular basis to the right-handed fields. U right, D right, S right, C right, B right, and T right. And since we are in a basis where the mass matrix is diagonal and real, then these are the mass eigenstates. These are the fields, the quark fields, that have well-defined masses. These are the things that our detector can tell it's this or that. Okay, it's not. If the thing that hit the detector has a mass, as we'll see, of 172 GeV, it's the top. Okay, the top doesn't hit the detectors because it decays before it hits a detector, but in principle. So here are the names that we give. So in the end, this will be Dirac fermions, right? It has only Dirac masses. So it's the same name for the left and right hand, up, down, strange, sharp, bottom, top. And there is a convention, which is which. It's by the order of their masses in QCD. If you add QED, they will also separate to two groups of different charges, but in QCD, it's just the masses that distinguish between. All of them transform in the same way under the Lorentz group. They are spin half particles, and under the SU3 group that we imposed, they are all triplets of SU3. The only thing that distinguishes between them is the mass, and this is the order of masses by which we call them their names. And since they are Dirac fermions, we can write it in the language, the full Lagrangian of QCD, in the language of Dirac fermions. So kinetic term for the gluon field, kinetic term for each of the 6 Dirac fermions. Again, what d mu is and what g mu nu a is dictated. And a mass, 6 mass terms, diagonal mass terms for each of them. So Q stands for this list of 6. So this is the QCD Lagrangian in the mass basis. So, what's the spectrum? It's not such a trivial question actually, because as we have 6 left and 6 right-handed triplets, then from the equation that I presented before, too quickly and very quickly for the running of the coupling constant, you should believe me that that equation tells us that GS becomes larger the lower the energy, larger and larger and larger. And at the end, at the scale of about 300 MeV, it becomes so large that we cannot do perturbative calculation. And usually when, this is a side comment, but it's important I think, if we cannot do perturbative calculation, it often means that we are not using the right degrees of freedom. And when we go to very low energies, indeed the quarks are not the right degrees of freedom, hadrons are, mesons and baryons. The proton, the neutron, the bound state of quarks. And so the spectrum at low energy is the spectrum of these bound states of quarks. So here I will discuss the UV spectrum, the thing that appears at high energy, where the quarks are and the gluon are the right degrees of freedom. So what we have here, there we have a massless SU3 color octet vector boson that we called the gluon, and we have 6 massive SU3 color triplet Dirac fermions, each with its own Dirac mass, MQ, and these are the 6 quarks. So that's the spectrum of the model that I presented. The masslessness of the gluon is because of the gate symmetry. Cannot write a mass square term that is invariant under a local SU3. And the Majorana masses are 0 for these because they are in a complex representation of SU3, the triplet. And the Dirac mass is not 0 because it's a vectorial theory. I can match the quarks to pairs of left and right that transform in the same way. The interactions. I have an interaction term for each of the quarks coming from the covariant derivative, the term that is not the partial derivative, but the other one, it's written here. It has a gluon field, a quark and anti-quark field. It's this here, represented here. This is the gluon, this is the quark and anti-quark. And from the kinetic terms of the gluons, I get both terms with 3 gluons and with 4 gluons, so I have this type of vertices. And again, the amazing predictive power of local symmetry is that all of these, for any pair of quarks, for any 3 or 4 gluons, there is just one parameter. So in principle, all processes that are mediated by the strong interactions depend on this one parameter and the quark masses, okay? But the interaction itself depend on this one parameter. Phase space, etc., depends also on the quark masses. So one and only coupling here. And these interactions here are vector-like. If a left-handed charm comes in and out, or a right-handed charm comes in and out, it's the same strength of interaction. So for each of the 6 quarks, that's what it means vector-like. It's diagonal. There is a UU bar, DD bar, TT bar, etc. There is no off-diagonal. There is not up quark coming in and top quark going out. No such thing here. It's universal. It's the same strength of interaction for UU bar, DD bar, SS bar, etc. And it conserves parity, charge conjugation, and CP. We did not impose them a priori. It's a consequence of the symmetries that we impose. So these are the interactions of the model. It has 7 parameters, 6 quark masses, and a single coupling constant. Instead of GS, we often use alpha strong, which is G strong squared over 4 pi. So these 6 masses are, instead of this complex 3 by 3 matrix, which has a priori 18 parameters, so only 6 combinations of these are of physical significance. And quark masses is a complicated topic that I will not enter. With some definition that is not actually the same for all of them. It depends on whether they are lighter than 300 MeV, heavier than 300 MeV, or even something super heavy like the top. With some definition that you can find in the particle data group, these are the values. They are very different from each other. The heaviest is 172 GeV, and the lightest is almost 10 to the, or a little bit more than 10 to the minus 3 GeV. So, yeah, some 5 orders of magnitude between the lightest and the heaviest. And the strong coupling constants at the scale mz, where it's perturbative, has a value of about 0.11. Remind you, it becomes larger the lower the energy. At about 300 MeV, alpha S becomes of order 1 or 4 pi. I mean, it runs there very quickly, so it doesn't matter much whether I say 1 or 4 pi or whatever. Accidental symmetries. Yeah, so accidental symmetries, the kinetic terms usually have a very large symmetry in them. And the accidental symmetries, it's a point I didn't mention, are always a subgroup. If they are a subgroup of the group of the kinetic terms. And so here, the quark mass terms break this large symmetry of the kinetic terms into a U1 to the 6th symmetry. The terms that appear involve UU bar, DD bar, CC bar. They do not have UD bar or BC bar, and so it's straightforward to see from the Lagrangian that we wrote down here that there is a U1 to the 6th symmetry. Transformation of U by a phase is a symmetry, and of the B with a different phase is also a symmetry of this Lagrangian, etc. So it has this U1 to the 6th, which gives predictions that are not realized in nature, and we later understand why. We said that the lightest particle charged under a symmetry is stable. Now, each of the quarks is the lightest transforming under the U1Q, okay? Bottom is the lightest transforming under U1B. And so this predicts that all of them are stable, and it does not allow off-diagonal things. So UU bar goes to CC bar is allowed because the initial state does not have any charge under any of the symmetry, and so here. But UC bar to CU bar is forbidden because this under U1U times U1C is 1 minus 1, and this one is minus 1, 1. So it violates both U1U and U1C. So it's forbidden, and we will see why these predictions are not realized in nature. So definitely they do not go by the strong interactions. That remains true in the full theory, but we'll see that it's the weak interactions that break these symmetries and actually keep one subgroup of this, U1, usually called baryon number, where all quarks transform in the same way. So instead of each of them independently, they all transform with the same phase. Then this is the remaining symmetry of the standard model, of which QCD is part. But the QCD interactions are the strongest, and therefore ingredients of these accidental symmetries are actually good approximations to many things that happen in nature. Confinement. Okay. It's time, and I think I mentioned it, so I'll just mention it here. So in the end, we don't see free quarks. We only see bound state of quarks in nature. The simplest are mesons, made up of quark and antiquark. A little bit more complicated are the baryons, made out of 3 quarks, and the antibaryons made out of 3 antiquarks. So all of these states that we see in nature are singlets of SU3. Mesons, it's 3 times 3 bar, which has in it a singlet. Baryon is 3 times 3 times 3, which also has in it a singlet. Antibaryon, the representation under SU3 is 3 bar times 3 bar times 3 bar, which also has a singlet. So all states in nature, so-called hadrons, are singlets of SU3. And this is understood on the basis that the coupling constant becomes larger at low energy. I will not go into the details of confinement, but we have a qualitative understanding of why we don't see free quarks. You take them apart from each other, you take a quark and antiquark, try to make them distant from each other. So low energy is equivalent to larger distance, and it costs you so much energy, the strong force wants to bring them back together, that at some point it is economical to nature to bring a quark-antiquark pair from the vacuum, put the antiquark together with the quark to make a color singlet, which is therefore not subject to the strong interaction. And on the other hand, the Q from the vacuum with the Q bar, combining into a bound state, if you want, of another meson, also not subject, and then there is no more force trying to bring them together. So that's confinement. And it's related to this running of the coupling constant, which is the main reason why I told you about running coupling constant. Okay, let's skip QED stand QCD and leave you with this Lagrangian of QCD. The number of parameters, the accidental symmetries, the definition of what is the field strength, what is the covariant derivative, are all dictated by the invariance under a local SU3. So again, a very impressive predictive power to local non-abelian symmetries. Okay, we'll stop here. Okay.
Questions?
It was too complicated for 1.5 hours. Okay.
It's a stupid question. Anybody has any naive or stupid question that they want to ask? Over the break then.
Okay.
It's time. Meet for tea and then come back.